So previously we looked at linear regression, and linear regression was when we were interested in plotting. In this situation, we were plotting a continuous variable against a continuous variable, and given a value of x, could we predict a value of y, and also how much of x explains the variance in y. We looked also at how significant our result was, and there we were looking at the F distribution. This session, we're going to look at logistic regression, and this is only different from linear regression in the way that we present our response variable as a binary variable. So, we have a continuous variable or multiple variables as before, as our predictor variables, and in this case, our response variable is either 0 or 1. And actually, we can see that if we plot our data, it would look something like this. So this isn't just a straight line of data points going up. You're either in one state or the other. And, we could go back to our example of number of cigarettes smoked per day and whether you will develop lung cancer, yes or no. So this goes into our supervised classification problem. So again, we in the introduction slides, we had 3 specific problems we would like to tackle in machine learning. And that's regression, which is linear regression. This is classification, supervised classification, which is a bit odd because it's got regression in the name, logistic regression. So that tells us that we are still going to try and fit some distribution to this type of data that will allow us to approximate a yes-no situation. So there will be some sort of distribution that we can apply to this problem. And I'd like to introduce, obviously, that we have yes or no, but we can have a probability of yes or no. So, so what we're going to do is frame logistic regression in terms of not only, and this goes for actually any supervised machine learning technique. Not only are we interested in the class labels, yes and no, but we're also interested in the probability of being predicted as either yes or no. And, what we were doing in linear regression, we were trying to plot a line of best fit, and if you were to plot, if you were told to only plot a straight line through this data to describe it, this would be the best you could do, the straight line. I think you can clearly see how we've taken this from the line of best fit in linear regression and applied it to this data. The only thing I would say, though, is that this would assume that the number of cigarettes smoked per day, there's a linear relationship between the probability of developing lung cancer, yes or no. And this is not quite correct because in low values of X or number of cigarettes per day or high values of X, if you just smoke 1 cigarette per day here, compared to someone who smoked 2 cigarettes per day, is there a linear increase in your risk of developing lung cancer? And this is often not the case. You would have stagnation of our response variable at low and also high values. So similarly, if we have someone who smokes 99 cigarettes per day and someone who smokes 100 cigarettes per day, really you wouldn't expect much difference in their risk at all. But in a linear line of best fit, that would say you would expect more. It's a linear relationship. So actually, what we would like is a function which can approximate at low growth for low values of number of cigarettes per day or our predictor variable, and also low growth when X is high. And what we'll find is that in the middle, that's where you usually see the growth. There'll be like a threshold where things start to increase more rapidly, but it's certainly not at the extremes of our continuous variable. So what function can we use to do this? We know that it can't be linear, and it must have probabilities built in. Again, linear regression doesn't have probabilities built in. It's infinite, because if you remember the y-axis intercept, That can go on and on and on, depending on how you scale and how you optimize M and C. And consequently, the line just continues going up. So linear regression, the linear function, can't approximate probabilities in general. And yeah, we're going to be doing regression. So it definitely is a function. We're trying to describe our data using a function. It's still regression, but we're going to turn it into a classification problem. So I've already said that we're going to be discussing probabilities. And if any of you have come across logistic regression before, it's a very common technique that's used in traditional statistics. So I'm going to try and unpick this so that hopefully I'm not confusing that they're two separate models. They're the same thing. Logistic regression is just one thing on its own, but it has two edges to its sword in a way. So I'll start off with talking about traditionally how logistic regression is used in statistics, and then we'll look at how you can use it in machine learning, because it's the same technique, but you can repurpose it to solve two different problems. And to do this, we need to have a conversation about odds and probability. So we know we're interested in probability in our classification problem, but usually I think logistic regression in stats, they're more interested in odds. So the results of logistic regression can be reported in two ways. And in one way, if it's expressed in terms of probabilities, you're looking at supervised classification. If it's expressed in terms of odds or an odds ratio, as in, in regression, this is describing our data. This is using traditional statistics. So you might see something like this. So you might see that a study found that developing lung cancer in smokers had an odds ratio of 2. So this means that smokers are twice as likely to develop lung cancer. The odds of people who smoke is twice as high as those which don't smoke. So this is a really common thing. I mean, you'll see things like this in newspaper headlines, like lines like this, and this often comes from, or at least it can come from, logistic regression, where the results are being reported as an odds ratio, or the odds of something happening. So this is logistic regression at work here, but you may also read something like this. So the algorithm was able to predict lung cancer in patients to 87% accuracy. And so when you look at these two sentences side by side, you might think, well, these are two different algorithms. The results are expressed in such a different way that this isn't the same algorithm, but it is the same algorithm. This is logistic regression in both cases, but one's expressed in terms of odds and one's expressed in terms of probability. So, some of you might have already, I'm sure you would have all seen phrases like this, and logistic regression can give you this. But we're more interested in this second case. This is classification, okay? So, typically we would think of this as a regression problem, but you can repurpose this. So how do we do it? Well, the first thing is to understand that odds, they do not equal probability. I know they sound like the odds of something happening is like it's intrinsically got probability built into it, which is true, but they're not exactly the same. So let's just talk about odds and how we can reframe odds in terms of probability, so that depending on the problem that we have, we can use logistic regression and we can give our results in either terms of odds or probability. So it's flexible. So let's understand this relationship and why they're different. So odds are the probability of something winning. So if we look at this example here, the odds of Liverpool winning is 4-1. This means that in 5 matches, Liverpool are expected to win 4 times and they're expected to lose once. So that's what that means. So odds, pretty simple. The probability, however, of Liverpool winning is 0.8 or 80%. And you can see the difference. The only difference is in the denominator, because in odds, we just had in the numerator one outcome, and in the denominator, it was the other outcome. But in probability, the probability of Liverpool winning is one outcome divided by all of the outcomes, and that includes Liverpool winning. So odds and probability are different. Odds are the ratio of one outcome over the other outcome. And probability is the ratio of one outcome over all other outcomes. And you can probably guess that odds and probabilities can be related because logistic regression can output things in odds or probability, so they must be related in some way. And let's just see how we can build this up. So the odds of winning, let's say, are 5 to 1, which equals 5. That means that the probability of winning is 5 over 6. So again, if this is the number of times expected to win, it's 5. Number of times expected to lose is 1. So we just add those two together to get our denominator there. Which means that the probability of losing is 1 over 6. And you can work this out, which it actually equals 1 minus the probability of winning. And we can see this here. So if this is all probabilities, i.e. 1, minus the probability of winning, 5 over 6, we're left with 1 over 6. So we can express the probability of losing in terms of the probability of winning. And what we'll see is that the probability of winning divided by the probability of losing is the odds. So let's see how this works out. If we have the probability of winning is 5 over 6 divided by the probability of losing 1 over 6, and the way you divide fractions is you just flip the denominator and then multiply the two together. And we're left with 30 over 6, which equals 5. So the probability of winning over the probability of losing equals the odds. So this right-hand side of the equation, these are expressing odds in terms of probability. So probability of an outcome can be related to the odds of an outcome by this equation. So the probability of one outcome, it doesn't matter which one, is divided by 1 minus that probability equals the odds. So this means no matter how the results of logistic regression are reported to us, we can interpret the results as odds or probabilities. And so this is how logistic regression is able to express its results in different ways that may seem like a different algorithm has been used, but actually it's the same algorithm. So before we go on, we're going to try and understand where the word logistic comes from in all of this, because so far we've got odds and probabilities, but why does logistic come into this? Well, if we have a look at odds, they have an undesirable property. If we look at any odds where the numerator is smaller than the denominator, the corresponding value will always be between 0 and 1. So where the numerator is smaller than the denominator, the corresponding value, you work that out, is always between 0 and 1. However, if the denominator is smaller than the numerator, the other way around, you can see that actually the values, they just balloon up. So this is undesirable because, what this says is that the magnitude of a 10 over 1 is the same as the magnitude of 1 over 10. And that's not really useful to us. We want these magnitudes to be the same. And the way to do this is to take the log of those odds. And as you can see here, log of 1 over 10 equals minus 2.32, and log of 10 is 2.32. So this is where logistic regression gets its name from, in part. Where often the results are expressed in terms of log odds first, and to obtain the raw odds, you would have to exponentiate these log odds. So when you hear a line such as people who smoke have an odds ratio of 2 in terms of developing lung cancer, those odds started out life as log odds. And that value of 2, they're twice as likely. They've exponentiated the log of the odds. So this is useful because we can now express our odds in a more linear way, because obviously this isn't a linear function, but this is a linear function. So because we now have a linear response in terms of odds, we can do regression, a nice simple regression. And this is what it is. So if this is the log of our odds, again, we can just equate this to mx plus c. a nice linear function, linear response against a linear equation. Yes, so we can relate the log odds of something happening. So we were looking at winning a match to a variable via regression, where our predictor might be percentage of possession of the ball, which is a continuous variable. Or maybe even other things. So, if you have multiple logistic regression where you have multiple values, features which might predict the odds, total amount of transfer fees within the squad. So Manchester City, they spend loads every year. Is there a correlation there? So we've discussed how odds come about and how logistic regression gets its name, and we can relate odds to probability, which is good because in our lung cancer example, we were interested in the probability. What's the probability you will develop lung cancer? And if the probability is above 0.5, then we might say that we'll classify you as, in the binary case, that you will develop lung cancer based on that probability. So this is what we're interested in. This is the setup. Again, here are our data points. We have a continuous variable plotted against a binary, and we have this situation. And not only can we classify as yes, you will develop lung cancer, or no, you won't, we can associate a probability with that. And the way we do this, remember, we had our log odds regression. What we're going to do is take this equation and solve for P, because currently logistic regression, the logistic regression equation is expressed in terms of log odds, but we would like to rearrange this to express our result in terms of probability. So let's take our logistic regression equation. And first thing we can do is we can exponentiate both sides. So we get rid of this log and we exponentiate mx plus c. And then we can move the 1 over p over to the side by multiplying both sides by 1 minus p. We can expand that out as so. Then we can take this term over to the left-hand side by addition, and we can factor it. And then lastly, we just move everything in the brackets. We divide by everything in the brackets, so we move it over to the right-hand side. So now we've taken our logistic regression equation, which was previously expressed in terms of log odds, and now we're expressing this in terms of probabilities. And this introduces the logit function, or often called the sigmoid function. And it's like so. So we were explaining before that we would like to have slow growth at the extremes of our variable, our continuous variable. And what we tend to find is that you'll get faster growth as you start to increase this. You'll get to a point where the risk just saturates and you get slow growth again. So this is exactly what the logistic equation does when you put it in terms of P, when you express it in terms of P. And so as you can see, depending on where you are on this, on the y-axis, this is our probabilities. So the logistic function takes a continuous variable, x, and the response is between 0 and 1. So this is ideal for our scenario. If we remember that in linear regression, m was the gradient or the slope, and c was the y-axis intercept, we still have these terms here. Here they are. They're just slightly different. They're exponentiated, and they appear in both the numerator and the denominator. But what are m and c doing in the logistic regression? Well, m is going to squash this curve. So if we start off with m equals 1, the black line here, and then we keep increasing m, it will squash this curve. So again, we're allowing hardly any growth for a lot of the variance in x, only where you reach this threshold where you start to increase a very steep increase in growth. So m, the gradient in the linear regression, here in logistic regression, it squashes the curve into different shape. And m equals 0, by the way, I should have put this in the graph. It's just a straight line. M equals 0 is just a straight line, which is what we drew at the start of this lecture. So, logistic regression, they can approximate, it is not a linear function, but it can approximate a linear function with certain values of m. C, which is the y-axis intercept in linear regression, it's similar. It just shifts the curve, shifts this logistic curve in a certain direction. So that's what M and C are doing. And again, like in linear regression, here we would like to find the optimum values for M and C such that it describes our data in the best possible way. So how do we do this? In linear regression, we use linear least squares. We looked at the residuals. We took the sum of those, so the squared sum of those residuals, SS fit, and we use that to calculate our R squared. But we don't have a distance in the y direction here because it's a binary variable, so we can't calculate SS mean, which is the variance in y. So what we're going to do, we're going to use an all-purpose method called maximum likelihood estimation. It can be used for any distribution. So we have our logistic function here is a distribution. We had an F distribution. We have a normal distribution. Maximum likelihood estimation can do the following for any of these. So it would say, I expect to see the majority of these data points when I use a certain distribution. I have certain values of M and C where all the data points that I observe can be explained well by the distribution I'm fitting to it. So let's just see how this works with the normal distribution, because everyone should know the normal distribution. We have our continuous variable X, and most of our data points, they converge to the center. So this is the average. We'll end up with some curve like this. So this is actually not a great fit because our average should be around here. The peak of this curve should be around here because this is where all of our data points are clustered towards. And, but we could take this distribution and we could use maximum likelihood estimation to say, so here's our mean and our standard deviation. We could use MLE to explain and say that, well, these data points here, it would be unlikely to see these data points given this distribution, because if you look at how it tails off, this could be 0 or whatever. We would only likely see, maybe not even that one, these data points. These ones we wouldn't. And we would like to find a function which would say that you're likely to observe the majority of these data points using a certain distribution, which might look like this. So we have a larger standard deviation. We can see that our average is shifted towards the center. And really, these data points at the extreme values, we're obviously less likely to observe these. However, this distribution would say we're more likely to see the majority of our data points using this distribution than this distribution. So that's what MLE does. It just iterates through different values of, in our case, M and C to control the shift and the gradient to find the distribution which approximates our data the best. So that's how you do it with a normal distribution. You could do this with an F distribution as well. And indeed, actually, linear regression, it can be solved by MLE, maximum likelihood estimation, like we're doing here with the F distribution. You don't have to use linear least squares. You could solve it in this way. But in logistic regression, because we can't do linear least squares, we are stuck with maximum likelihood estimation, which is still really good. It's not like second best to linear least squares or anything like that. But, we can just, if we have two different curves here with different values of M and C, we can clearly see that the black line where M equals 1 and C equals 1, we are more likely to see the majority of our data points using this black distribution here than we are with the red distribution. So, you can use MLE to solve this problem. And as I said, anything where you have a distribution, to describe your data, you can use this really simple method, maximum likelihood estimation, to fit the best distribution. Okay, so we understand now that to express this problem in terms of probabilities, we need the logit function, or sigmoid function. We can control things like how we squash the curve and shift it with M and C, we optimize it, and we can use maximum likelihood estimation to arrive at the best values for M and C. So that's fine. We can take some data, we can fit our logistic curve or sigmoid curve to our training data. And then, of course, we can use that to make predictions afterwards. So, here's a curve that we've arrived at based on maximum likelihood estimation. And this works really well as a classifier because, we've got some in the no lung cancer people, the number of cigarettes per day, you can see there's a big gulf here between those that do smoke. And we can equate this for this data point here. They may have a 25% of developing lung cancer. So we can have a decision boundary, I don't know, which something arbitrary, like if it's less than 0.5, then you won't develop lung cancer. And the reason why this is a brilliant classifier, or rather our data is so nice, is because we have this large classification boundary. We could set the threshold at any point along this curve within this box, and it will get 100% accuracy. It splits the data so well. However, and what you'll find is actually most implementations, when we look at this by default, they will compute the accuracy based on this 50% threshold. However, real world data is not quite as nice. So we have some overlap here. In this case, we have a data point where they don't smoke that much, and you predict them to have only a 20% probability because this is where they lie on the curve, intersects the curve. However, this person did go on to develop lung cancer. So, this could just tells you that, number of cigarettes smoked per day is not the only thing, you have genetic liability and so on. Conversely, we have someone who smokes a lot. They have 90% probability using our model of developing lung cancer, and they don't go on to develop it. So real world data, this is how we introduce error. There's no boundary within here, clear boundary, which can separate these two classes of data. So if we know there's going to be some error in our classification, then we need to assess the accuracy in some way. So just take this little toy example. We have our number of cigarettes smoked in our raw data and whether they did or didn't develop lung cancer. What we can do is we can take a proportion or subset of our data to train a model and arrive at a logistic curve where the values of M and C have been optimized with maximum likelihood estimation. So we take a subset of our data to get this logistic curve, where we optimize M and C with just this data. And then we want to test how good our model is, or rather find out how much error is in our model with this test set. So this hasn't been used for training data. We're just going to feed this in as what's called test samples or test data, and compare the predicted value for these people with the actual value, with the ground truth. So, this is the actual label. This person, however many they smoke, they did go on to develop lung cancer. That's actually what happened. When we plug this into our model, it's going to give us, firstly, a probability of developing lung cancer. And then based on our cutoff point of maybe 0.5, we'll assign them as lung cancer. So we can compare these two, what actually happened to what's predicted. So yeah, we have some training data that we optimize our equation on. And in this example, we might say that, okay, the best value for M was 0.12. The best value for C was this. And given some test data, we take in the number of cigarettes they had, i.e. X, and plug the value in. So there we go. And this would work out as 0.39, so 39% chance of developing lung cancer. And we take this prediction of what actually happened. And there are 4 scenarios. So the first is true positives. So the model predicts lung cancer, and the person actually went on and developed lung cancer. So that's a true positive. We were able to predict that someone was going to actually develop lung cancer. We have a false positive. So the model predicts lung cancer, but the person did not develop lung cancer. It's the opposite. We have a true negative. So the model predicts no lung cancer, and the person doesn't develop lung cancer. So, in the negative case, they didn't develop lung cancer, and we predicted that to be true, which it was. And then the flip side of that is a false negative. So the model predicts no lung cancer, but the person actually does go on to develop it. So, wherever's got true in the name, this is correct. But whenever it's got false in the name, we're introducing error. And the way to look at this, and this is what we'll produce something called a confusion matrix in our notebook, is we can take our actual results. So, they were actually positive. And we can take our predicted and plot them against each other here. So in the top left, where it's positive, we have true positives. So predicted as positive, and it actually was positive. We have false negative, predicted as negative, but they were actually positive. Do you see what I mean? So you can go through these, and here are our types. So we have a type 1 and a type 2 error. And our final accuracy is computed by the number of true positives plus the true negatives divided by all outcomes from this matrix, which is this equation here. So this is good. We can use training data to optimize M and C and get a nice logistic curve. Then we can test, and we should always use an independent test set to assess our final accuracy. And we can do that like so. Yeah, so this is really, really important. Technically, you can get a confusion matrix using just the training data. However, we never report accuracy on the training data. And the reason, there's a few reasons for this. The ground truth labels, they're accessible to the model during training data. So, it's learning from the ground truth labels directly. It has those available to the model. And so what you'll find often, if you look compute accuracy on the training data alone, where the labels in the training data have been used for prediction, that will lead to inflated accuracy. What we want to do during testing is hide these labels during prediction. Therefore, we can make a prediction where we're blindfolded to what the actual ground truth was, and we just compare them side by side, which is a much better way of doing it. So, we only ever use an independent test set that has not been used for training to evaluate our model. Okay, so that's logistic regression. In summary, logistic regression can be used to predict log odds that are typically you would see in statistics or newspaper headlines or so on. And it is regression. We are fitting a line to some data still. It's a sigmoid, but it's still some function. The other side of the coin is logistic regression can be used to predict probabilities, which can be used for classification purposes. So for all intents and purposes of this course, we are interested in the second case. We'd like to express the results of logistic regression in terms of probabilities. Just like in linear regression, it's almost the same equation. We are optimizing coefficients, M and C. Yes, and even though regression is in the name, in this case, we do fit a sigmoid to our data. It can be used for classification. So it's kind of like a link function from the world of traditional stats into machine learning. And just be aware that algorithms, I know you've probably all heard of artificial neural networks. They're most famous for classification, how Tesla are using neural networks to teach cars how to drive, don't drive into that because it's a lorry, classification and so on. But actually all these algorithms, fancy algorithms like neural networks, they can also do regression as well. So I guess the point I would like to get across is that statistics and machine learning, they're not worlds apart at all. They use some of the same techniques, and I think logistic regression is definitely a way to describe that. It's the same equation. you just reframe the results in a certain way, and you go from what might be a traditional regression problem to a classification problem. So if anyone says machine learning and stats, they're completely different, that's just not true. Okay, yes, and there we go. So let's look at the notebook and see how you would run logistic regression in R. So again, as I said before, tidyverse, maybe just out of habit, I just always put this in, but it's got a lot of useful libraries. So we're using some data directly from Kaggle. You can add data, and you can go and find data you're interested in. So diabetes. Okay, so this is one that I uploaded, and it's available to you all now. But there's others you could use, and you can simply add this into your notebook by pressing add, and you'll end up with something like this. And here you go. So we have diab.csv. So we're going to use this today, and let's have a look. So yeah, we input our data like this. This data set was a bit odd, even though it was it's saying it's a CSV. The separator was, I believe, a space. So what we're saying, oh, sorry, it's quote, no quote. So the fields are delimited by a quote. So that's what we're saying here. So we run that, and we can explore our data. So we can say view. Actually, you don't even need to do this in Kaggle because it automatically calls that function. There you go. So we can see, what our data types are and so on. And what we're interested in is predicting diabetes, yes or no, 1 or 0, against continuous variables. Yeah, so this, just to be aware, you should always explore your data. This is a tidyverse equivalent. Dplyr is a library within tidyverse, and this is its version of str. You can see it's really similar. We can do summary of the data frame as before, which is quite handy because you get to see the means of certain columns and so on. Patient ID, obviously we wouldn't want to use this for classification because it's arbitrary. But anyway, and again, you can specify the number of columns. So we take the head function, which usually gives you the first 6 rows, but now we can say output the first 10. Xtabs is quite a nice function for data exploration. You can input certain values and get contingency tables. Again, so this is quite, just useful ways of exploring your data. Okay, let's get into the classification. There's one thing we need to do before we run the algorithm, which is here. That is to ensure that the column that we're trying to predict, the binary column, is a factor. So any machine learning technique in R, they usually want your target variable to be a categorical variable, i.e. a factor. What we see here is that is an integer, and usually it'll just throw up an error saying, or attempt even to do regression. I predict a continuous variable. By telling it is a factor, a lot of these algorithms, they know immediately then they're doing supervised classification rather than just regression. So that's what we can do. We can just turn that column into a factor. And here it is. So generalized linear model, that's the function before we just use linear model in linear regression, but it's exactly the same. We just take our target variable, use a tilde and say, I want to express that in terms of BMI and age. This is multiple logistic regression. And you say family equals binomial. So there are other parameters in here. So if you look at the GLM documentation, if I just run that, so question mark GLM, we can get the documentation. This is true for any function in R. Just put a question mark before it. Family, so we can see that there are different types of families there. I think we can probably choose. Doesn't really give us an example. Doesn't matter too much. Binomial means logistic regression. You can do something called a Poisson regression, which is when you're modeling rates, or you can have a linear regression. So you can have linear in here as well. So just by this parameter here, family just tells you which type of regression you want to do. So we run that, and this is our output. It looks really similar to that in linear regression. So we have residuals in X, not Y. These are our log, the coefficients here. This is a log odd, okay, log odds. To get the true odds, you need to exponentiate this value. You get the standard error. Z is the coefficient, or the log odd, divided by the standard error. So this kind of, think of this as way stability. So the larger the Z is, the more stable your prediction is. We also have our P values. A few things. So yeah, this might look a bit strange. Number of Fisher scoring iterations. This basically just says how many times did we have to iterate values of M and C in our logistic regression equation to find the best distribution. So this ties into maximum likelihood. We had to choose 4 different iterations of optimizing M and C to arrive at the best one. Okay, so once this is done, we save this into this object called logistic, for want of a better name. We can create some new data. So we just create a data frame, which is just that. And we're going to plug these in, the BMI and the age, into our logistic regression equation. And there it is. So with these values, you would have a 22% chance of developing diabetes. Now you can add more features. And again, you can put them in manually, or you can use the dot notation. So yeah, obviously I'm giving this lecture the week after we actually did the lectures, and some of you found out during the lab that by including all features, you get a warning that the maximum likelihood estimation couldn't converge on an appropriate distribution. So that's something that logistic regression, although it has MLE inbuilt, which is really good, if you put in too many features, you've got too many features, pulling this distribution this way and that way, that sometimes it can't converge. So sometimes you have to reduce the number of features you use in logistic regression. After all, is a simple equation. But anyway, you can see here that we have all of our features in here. So I'll just here you go. So we can see, which feature, when you relate it to diabetes, has the highest log odd value. Some have a negative log odds, a protective effect, if you like. So it's really similar results to linear regression. Again, I create a data frame of all those, and I can predict that. So with these particular things, feature values, this is your risk of 55%. So you might conclude that that goes above the 0.5 threshold. We would say, yes, you would develop diabetes. However, we talked about training and testing earlier, and that's what you should do. So we should take our data set, DF, data frame, and convert it into a training set and a test set. So here what we're doing is we're setting up at 75% training set, and 25% of our rows go into a test set. You can use the sample method. So we're going to shuffle our data first. So basically, DF square bracket, we're subsetting our data, and the number of rows we want to subset by are the number of rows, but we're going to shuffle them. Okay, and again, we use all columns, so we leave that blank. And then we say our training set consists of the first row up until the 576th row, and our test set is the 577th row all the way up to the last row in our data set. So that's how we're going to do it. We're going to get our train test split. And this is good because at the moment, we're only using single values or single rows of data to do prediction on. But we actually want to compute this confusion matrix. So taking a large test set and estimate our error. So that's what we're going to do. Take our training set to train this on, and we get values here, which is good. But then we take in our test set into the predict function. So instead of just one row of data, like we were doing here. We're going to put all of our rows of data in. And this is another really good thing about R. I talked about lazy evaluation before. Yeah, everything in R is a vector. Like absolutely everything in R is a vector. I don't have to write a for loop. You know, you might think this function here, predict, that is taken one row of data. So maybe I should have to write a for loop to put in more rows of data. But no, everything in R is a vector. So all these functions, they're vectorized. I think this is one thing which I quite like over Python. In Python, you would normally have to write a for loop, or I know you can use the map function. But yeah, so this is a good thing about R. And what we output, we put in different type. Response, you could put in type raw, which gives you the log odds. If you put in type response, this basically says rearrange the logistic regression equation in terms of P, and out pops P. So for each person in the test set, you get their probability of developing diabetes. And lastly, to get our confusion matrix, we create a contingency table. And the first parameter are the predicted, or it doesn't really matter that they give you the titles here. So predicted is our first parameter, and observed, which is the ground truth. This is what actually happened. And you plot those against each other and you get our confusion matrix. So remember, to get accuracy, you sum up the true positives plus the true negatives over and divide it by all of the samples in the data set. So I'll leave you do those calculations yourself. Again, you can, just to practice, you can try adding the Wisconsin breast cancer data set. So you can add it here. So it's a pretty famous data set, just used for training purposes, and add that in and try logistic regression on that. So that is logistic regression. And what we'll look at tomorrow is probabilities again, but we'll be looking at naive Bayes. So until then, I will see you tomorrow.